This video is going to cover everything that you need to know for Unit 8 for our test on April 16th for my A day and April 19th for my B day. The timestamps are listed below, so you can skip around if you need to. This may be a long video because it does include a lot of stuff, but I do have example problems, so let's get into it. The first topic we're going to talk about is mass versus weight, and recall that these are not the same. Mass is about the amount of matter or number of particles that something is made of. Your mass will never change based on your location in the universe. So if I'm on the moon, my mass will be the same. Mass is just about how much and what you're made of. So a speck of dust has a small amount of mass, but on the moon it's going to have that same amount of mass, and your desk has a larger amount of mass. However, if it was on the moon, it would have the same amount of mass. Now, when we're comparing weight and mass, we have to look at gravity. Recall that gravity is a force of attraction between objects that is due to their masses. Me as a person, so Mrs. McCaslin, I have my own force of gravity based on my mass. It may not be as big as a semi-truck, for example. However, I do have my own pull. So this gravity, this force, is what can help affect my weight because my mass stays the same. But this force is what's going to change my weight. Now, weight is different because it is focused on the force exerted on that object by a local gravitational field. When I talk about local gravitational field, I'm going to use F of G. And for example, that is the gravity for that specific location. So on Earth, we have our gravity as 9.8, but the moon and Jupiter, they're going to have different types of gravity. Weight is dependent, though, on mass and the distance or the location. So recall that there are two factors that are going to depend on our amount of traction between these two objects, and that has to do with the masses of the objects and the distance of the objects. When we look at the mass and the distance, an example that we can look is this figure right here. If I have a greater amount of mass and I don't have a very big distance between me, I'm going to have a stronger pull or stronger gravity between my objects. Whereas if I have a little mass and I'm in that same proximity, my force will not be as strong because I have less mass. But if I have two extremely heavy masses or bigger masses and they're very far apart, that force is still going to be small because the distance is too great for it to be as strong when it is closer. Now, if I want to test mass without gravity getting in the way, we're going to use inertia. So inertia is about the resistance to change. So how could I move an object without changing the gravitational force? It's actually pretty easy. The gravitational force is going to be the same, but the resistance to change or staying in the same distance while you're moving is really going to help affect this. Now, we use this equation, and this is what is used to solve for the strength of gravity or the weight. So if I wanted to see how much I weigh on the moon or Earth, I'm going to find my mass in kilograms, and I'm going to multiply that with the gravity for that specific location. Since we had the opportunity to see this equation, why don't we do some calculations? So looking at number 1, we have a backpack that has a mass of 5 kilograms on Earth, and I want to know how much that backpack weighs in newtons. So we're on Earth right away. Earth's gravity, right, we associate with 9.8 meters per second squared. So I want to solve for my W. So looking at my triangle, what I'm going to do is I cover up my W, and I say, all right, I'm left with M and my G. So then I'm going to do W is equal to my mass times my gravity. I do W equals, and I find my mass as 5 kilograms, times my gravity of 9.8 meters per second squared. Plug that in your calculator, so do 5 times 9.8, and you get about 49. The unit on that is newtons. And that's my answer. So doing the same thing, let's do number 2. So how much does the backpack weigh on Mars if the gravity is 3.7? I'm still looking for my weight, and I'm still using that same mass of my 5 kilograms, except this time I'm using this as my G. So my G is now 3.7 meters per second squared. I do 5 times 3.7, and that gives me 18.5 newtons as my final answer. Oops. There it is. And that's all I need to do to solve. In the event I was looking for my mass, it would be a little bit different, and I would have to cover up my m, and I'd be left with w over g. But using the triangle is extremely beneficial in figuring out what equation I need to use. So now let's do Newton's first law. Galileo set the stage for Newton to come up with his laws. Galileo found about gravity, and he also found out about inertia, which is our resistance to change. So Newton built off of Galileo and came up with this. Newton said that every object continues in its state of rest or a constant speed in a straight line unless acted on by an unbalanced force. Or, simplify it, an object in motion will stay in motion, an object at rest will stay at rest unless acted on by an unbalanced force. An unbalanced force has to do with something that is causing it to stop and or move. So thinking back into our Penny Lab, when I released the cart, it hit a wall of sorts where the wall was the books. The books was my unbalanced forces because that is what's keeping my car from maintaining its inertia. It's stopping it. Or another example is if I had a soccer ball that was on the ground and I went and kicked it, my foot would be the unbalanced force because I am taking that ball out of rest. I'm taking it out of its inertia. Typically, forces are balanced unless it's trying to get it out of its constant speed or its rest. What's important to know, though, is that an object at rest is going to have zero velocity, meaning it has zero acceleration. That's why it's going to maintain its rest. But if I'm an object in motion, I no longer have a velocity of 0, but I'm keeping a constant velocity, so like a constant speed, meaning my acceleration will still equal 0. This is what causes me to stay in motion in the same speed and direction. So if I were to look at a couple of examples, there's this trick where you can pull the dining room table cover off of a table, and your plates and your candles and your glasses will stay the same. The reason for this is that these plates have their own inertia, and they want to stay at rest. But I'm forcing the blanket to break, or the tablecloth to break its inertia by using my unbalanced force, which is me grabbing it, and remove it with a force. So these are going to stay at rest, my plates. These are going to stay at rest, but I'm applying an unbalanced force, which is my person, to remove the tablecloth. Same concept. My car and my person, they have their own inertia, right? Along with my hat. But when I brake the car, so I'm going to brake it or stop it, this acts as my unbalanced force. And this stops my car and my person. However, my hat has its own inertia, so it's going to maintain its movement. Now that we've done Newton's first law, let's go into Newton's second law. Quick recap when I talk about direct and indirect. Direct is as one value increases, the other value increases. So I see a relationship that's directly changing at the same rate. And indirect is as one value increases, the other decreases. So I see an opposite relationship. Newton's second law of motion all focuses on acceleration. Acceleration of an object is going to be directly related to the net force, meaning as acceleration increases, my net force will increase. However, acceleration is indirectly related to the mass of an object. So as mass increases, acceleration decreases. So this is as mass increases. If my mass decreases, I will see an increase in acceleration. However, I see an increase and I see a decrease in the relationship. However, mass and force have a direct relationship, so as mass increases, my force will increase and vice versa. Basically, what I'm saying is as I have more mass, I will have more force that will take to accelerate an object, meaning I will have a less amount of acceleration as the result. So more force applied equals more acceleration. We can calculate this by using net force is equal to mass times acceleration, or F is equal to ma. We can plug this in the triangle, so I will have those on the next slides, but let's do a couple examples. So in this case, an object with a mass of 15 kilograms accelerates at 2 meters per second. What is the net force acting on the object? First, I need to figure out what equation I'm going to use. So I'm going to cover up the F because I'm looking for force, and I am left with F equals m times a. Now that I have that information figured out, I just have to plug in what I have. So I have a 15 kilogram object, so that's my mass. And I'm going to multiply that by 2 meters per second squared, which is my acceleration. There I get my force of 30, and I put newtons. That is all I have to do. Now let's talk about free fall. Free fall is without air resistance. So the only thing that I have acting on the object, if it's in free fall, is those that are only gravity. I don't have any friction. So in this case, if I were to drop a ball and I had no air resistance, the only arrow that I need, vector-wise, is my force of gravity going down. There is only one force acting on an object in free fall, and that's gravity, which we say is equal to 9.8 meters per second squared on Earth. So if I were to ask you an object is in free fall, what is its acceleration? You should be able to say 9.8 meters per second squared. The reason why objects with different masses are going to accelerate at the same amount, which we observed when we watched the video with the medicine ball in class, is that the acceleration of an object depends on two factors. It depends on the force or the weight, as well as the mass. So the inertia plays into it, because if we look at this example here, if I have one mass, I'm going to have an equal force to that. That gives me F over m is equal to gravity. But in this case, if I am going to increase my mass by 2, my force is also increased by 2. So ultimately my 2's cancel out, so I'm still left with that same relationship of F over m equals g. So now that we've talked about free fall with no air, let's talk about something that's in non-free fall, or something that will have air resistance acting on it. For the most part, air resistance is non-negligible for falling objects, meaning I have to make sure that I'm including it. So what happens to the acceleration of the object compared to a free fall? Well, let's find out. So in Newton's second law, when we were discussing non-free fall, anything that's considered non-free fall is when acceleration is less than g. So the only two forces that you will see acting on the object is going to be the following. We're going to have our F of g, or our weight, and then the other one we're going to experience is our air resistance, or our F of F. Air resistance acts up always, and Fg acts down. Your weight, or your F of g, will increase with depending on your mass, and your air resistance will increase with surface area. The story of the fall is in your notes. However, I'm going to explain it using this visual, so I will verbally be saying what is in the notes, but you can use the slides to reference at it. So in the beginning, the instant an object is falling, so if I were to jump out of an airplane, the only thing that I will experience really is gravity, as close to acceleration. So I'll have a force of gravity and little to no air resistance. So you could kind of see it as like a small arrow, kind of like this, or no arrow at all. But my force of gravity is greater. However, in the middle, I'm going to see that the air resistance on the object is going to build up. So my gravity isn't going to change. However, I'm going to see an increase, like a steady increase, of my air resistance. So I'm going to see this increase. As my speed is building up and my air resistance is building up, my acceleration, I'm going to see a decrease. So my acceleration decreases as my air resistance increases. And finally, my force of gravity for the last part is still going to be that same distance, but my air resistance will now be equal to my force of gravity. So this means that my acceleration is going to be equal to 0 meters per second because my net force, so me taking my arrows and subtracting them, is also equal to 0. This also signifies that I have reached what is called terminal velocity. This is also known as like a constant velocity. To solve for non-free fall acceleration in the equation, you're essentially, this messed up, is going to be A is equal to F of M, but in the event that you have two forces, you're going to take your F of G minus your force of friction all over your mass. So let's do a sample. We know our acceleration is equal to force over mass from our previous slide. So a 2.04 kilogram object experiences 12 newtons of air resistance. Determine its acceleration at this point. So to do that, I'm going to put my force, which is my 12 newtons, on the top, divided by my mass of 2.04 kilograms. So in your calculator, you're going to take 12 divided by 2.04, and it gives you about 5.88. And with your acceleration, your unit should be meters per second squared, and that's your final answer. Let's do number 2. Same idea where my acceleration is equal to force over mass. I have 46 newtons of force with 8.3 kilograms. I'm going to take my 46 divided by my 8.3, and I should get about 5.54. Again, I'm working with acceleration, so my unit should be meters per second squared, and that's all I need. Now, when I talk about terminal velocity, it is important to know that the mass of the object will affect it. So a lighter object with a smaller force of gravity will reach its terminal velocity faster because it doesn't have as much to overcome. However, because it is lighter, it's going to have a slower terminal velocity compared to those that are heavier objects. Now, a heavier object with a larger force of gravity is going to be slower at reaching its terminal velocity. However, because it takes a lot longer for it to reach terminal velocity, it has a faster terminal velocity opposed to those that are of a lighter weight of the object. Now let's look at how do I calculate free fall and non-free fall distances and speeds. So Newton's second law of motion, in the event that my acceleration is gravity, I am in what's called free fall. Now this means that I only have that one force, and it's the force of gravity acting on that falling object. So I have negligible air resistance or zero air resistance. This object is considered to be in free fall. So if it is where I give you an example saying that I have an object that is falling where acceleration, where force of gravity is the only force, I have no air resistance, what you should be able to say is that that object is going to free fall toward Earth at 9.8 or 10 meters per second. We do the 10 because it's easier to plug into our equation. Let's find out what is our distance equation. Now, when I'm looking at my distance equation and I'm in free fall, that means I'm going to use this equation of d is equal to 1/2 10t squared, or to simplify it, d is equal to 5t squared. So now if I were to drop something and it fell for 3 seconds and I wanted to know how far it would go, all I would need to do is take 5 times the square of 3, which is 9, to give me 45 meters. So now I can see after 5 seconds of falling what is my speed. To do this, you do have to find your distance first. So you're going to take your distance and equation and put your 5 squared in. So you get something that looks like 5 times 25. And that should give you 125 meters. Your last step is to take the 5 seconds and then divide it, because you're going to take distance over time. And you should get 25 meters per second. And then you're good. There is another equation that you can use, and that's only in the event that you don't have anything else, and that's 10 times t. But for the most part, you're going to be working with this equation down here. And last but not least, let's go over Newton's third law. Newton's third law states that whenever one object exerts a force on a second object, that second object exerts an equal and opposite force on the first object. So think about the Newton's cradle. As I have one of the balls approaching, my blue ball approaching my yellow ball, it's going to take that force and exert it on that yellow ball, but then that yellow ball is going to pick up its force. Now there are two forces that we use, and that's called our action and reaction forces. An action force is where object A exerts a force on object B. So in our example below, our action is the person is leaning against a wall. So object A is our person and object B is the wall. A reaction force is when object B exerts a force on object A. So in this case, the wall is exerting a force on the person. If I were to draw a diagram, I could say that here is my action, and the wall back on me is my reaction. Now, action and reaction have to be equal in strength, and they're always in the opposite direction because they occur in pairs. So here are a couple of examples. Action is tires pushing on a road, and the reaction is the road pushes on the tire. A action is a rocket pushes on gas, and the reaction is the gas pushes on the rocket. An action could be a man pulls on a spring, and the reaction is the spring pulls on the man. And last but not least, an action is earth pulls on a ball, and the reaction is the ball pulls on earth. So let's check. When you step off a curb, earth pulls you downward. The reaction to this force is A, a slight air resistance, B, non-existent in this case, C, you pull on the earth upward, or D, none of the above. Now in this case, I'm stepping off a curb, okay? So I'm gonna use, I'm stepping off a curb. So this is my foot on the curb. And in this case, the earth is pulling me down. So because the earth is pulling me down, my reaction must be that I am pulling back on the earth in the opposite direction. So that means that my answer is C. Now, I do have an action-reaction with different masses. In the event that this happens, the same force is applied to two objects. However, the greater mass object will have a smaller acceleration, and the smaller mass object will have a large acceleration. But what you really need to focus on is how do I illustrate my arrows for an action and a reaction. So that is everything that I have for you. If you have any questions, please let me know. But your study guide is an excellent tool and resource, and you may have questions that come from there. So use this video, use the Quizlet, and anything else that will help you be successful. But until the test, good luck studying, and I hope you have a wonderful day. Bye.